Hello, my name is Daniel Houston, and this is my Lab 3 study of a black hole. In this lab, we'll be dividing this experiment into two parts. In the first part, we'll find the unknown mass of a black hole by tracking the forces from a given star. Then, in the second part of this lab, we will use this mass of the black hole to determine the initial velocity that a spaceship needs in order to take off from a planet orbiting this black hole. Now, there are a few assumptions we're going to make with the first part of this experiment. The first part is the mass of the star orbiting, and this will be about 2.0 times 10 to the 30 kilograms. And the time interval for this will be about 1 day, which is about 86,400 seconds. The mass of the black hole will be determined using a randomized seeder and based off of an individual email. This mass of the black hole then affects the trajectory of the star orbiting the black hole and will make the net forces observable. We can calculate the net forces on the star by finding the velocities of the star to then find the momentum, which is the mass times the velocity of the star. And by using Newton's second law, we can then know the net forces on the system that are equal to the changes in momentum over the change in time. Before we look at my full code, let's look at some individual things in this part that I have pulled out right here. First, you can see the F net, which equals the change in momentum over the change in time. You can see in the first part about lines 157 through 175. And then in the second half, you can see the individual parallel and perpendicular forces calculated below. And at the bottom, you can see the mass of the black hole's calculation. This is my full code for this project. And this is the code running. As seen in the code, the mass of the black hole can now be calculated so that we have the net force, and the average mass of the black hole is 9.83 times 10 to the 30 kilograms. And we can rearrange the net force equation to solve for the mass of the black hole. Moving on to part 2 of this experiment, we must now determine the initial velocity of a spaceship off of a planet in order to fly around the same black hole from before without crashing into the planet. Now we will assume that the mass of the black hole is the same as before, with 9.83 times 10 to the 30 kilograms, and the mass of the planet will be 6 times 10 to the 28 kilograms, and the mass of the ship will be 7 times 10 to the 20 kilograms. We can find all the forces acting on both the ship and the planet using the gravitational forces, and we can track their orbits using the velocity and the position update formulas, as seen in this slide. This is the code that I used for the second part of this project. And this is the program running. Now, in order to escape the system of the black hole, we need the velocity to be higher than the escape velocity, but smaller than the speed of light. This was the initial velocity used to produce the following results. So, what does this mean? Well, with the net forces and its parallel and perpendicular components, these are different from the rates of change of momentum because the net force can only be inferred based off the observed data of the rate of change in momentum. However, the value for both of these are still equivalent. If you wanted to enter the orbit of the black hole, you must make sure that the initial velocity is not higher than the escape velocity. Additionally, you would need to make sure that the velocity will not cause the ship to crash into both the planet and the black hole. The value I used for the initial velocity to produce the following result is seen. In order to see if the ship would crash into the planet, I ran the program for several hours and saw that the planet and the ship did not collide. Thank you for watching my lab.